Okay, in Chapter 2, we dealt with rectilinear motion. That was motion along a straight line, but now we're going to extend those ideas that we developed there about position and then velocity and acceleration to multi-dimensions, to motion in space. And the idea is to replace the position vector x with a position vector r, which is a vector from the origin out to the location, our position P. It is a radial vector, much like polar coordinates, and that's why the r was chosen. And it is made up of components in the I, j, and k directions. That's the position vector P has a vector of magnitude x in the direction of the I unit vector and a vector of dimension y in the direction of the j unit vector and a vector of dimension z in the direction of the k unit vector, and these three vectors added together add up to this position vector r. So that is not a great stretch of the imagination to get there. And then the question of velocity, now that we've gotten position, velocity, just as it was the case before, is going to be the derivative of position, or the change in position with respect to time. And as we would so nicely hope, it comes out to be the case that when you take the derivative of r with respect to time, you are taking the derivative of this polynomial, where x, y, and z are functions of time, but I, j, and k are constants. And so when you take the derivative of each of those, it becomes just the derivative of the part that is a function of time times the unit vector in that direction. And so the result is, as we would have hoped, that velocity is equal to the sum of the x component of the velocity times the I unit vector plus the y component of the I unit vector and the z component of the I unit vector, just as we might have hoped. And acceleration also is just a matter of taking the second derivative of position with respect to time, and each of these parts of the polynomial behaves itself very nicely. Second derivative, or if you like, the derivative of the velocity with respect to time, and you get this expression which represents the a sub x, the component of the acceleration in the x direction, times the unit vector in that direction, plus the a sub y, and so on. And so it behaves itself exactly as we would have hoped. Next, the book deals with parametric equations, which always is a bit of a challenge for me, but it's really just a matter of introducing one more parameter. Instead of looking at y as a function of x, instead we will look at x and y as functions of yet one more parameter. And so the example that the book gives you is of this pair of parametric equations. We could, of course, have an expression for z as a function of time. And then the book takes that parametric equation and asks you what the displacement, velocity, and acceleration are at 2 seconds. And it's really quite straightforward that you are just going to substitute t2 for the time in these two expressions, and then you would get this much in the I direction and this much in the j direction, and that would be the statement for the displacement. And for the velocity, you just take the derivative of these two, and thus you would have dx dt, and that would be in the I direction, and dy dt, and that would be in the j direction, and that then would be the expression for the velocity. It should be a very easy task. Please complete this task and on your quiz, and then carry on. There is this checkpoint, which I would also like you to complete there on your quiz, that you have an object which in the first instance is traveling clockwise around this circle, and I want to know in which of quadrants it lies when the velocity is equal to this quantity. And then if it's going around it counterclockwise, that is, in this direction, in which quadrant does it lie when the velocity is equal to this quantity again? This would be the first, second, third, and fourth quadrants. So do those tasks on your quiz and then carry on. This picture ought to be familiar to you, and you ought to also be able to tell me what is being illustrated by this picture. And I wish, as I pause here, that you would jump into the fray and tell me. I wouldn't be there to know. But what we're seeing is projectile motion. There's a strobe that's going off, so every time the strobe flashes, we see where this red and yellow ball are at that instant. But what we're seeing is projectile motion, and what we learn from this picture is that whether it is kicked to the side or dropped, that it falls at the same rate, that the rate of fall is completely determined by the acceleration due to gravity, by the gravitational force, and is not affected by whether you are kicked to the side or just dropped without any kick at the beginning. And the key thing here is that in projectile motion you have these two independent but simultaneous behaviors. You have the accelerated motion downwards and the constant velocity motion horizontally. That you could also note that when between these two flashes, the distance that it's moved horizontally is the same as the distance it's moved horizontally there and here and here, that there being no acceleration in the horizontal direction, there is no acceleration. Similarly, this one, which starts off with velocity 0 horizontally, continues to have velocity 0 throughout the fall. So, in dealing with projectile problems, which I hope you feel very familiar and comfortable with from last year, basically you have an equation for the horizontal behavior in terms of horizontal velocity and horizontal acceleration, which does simplify because there is no horizontal force, there is no horizontal acceleration. We get this expression with, instead of the initial velocity in the x direction, I have the x component of the initial velocity. And this expression for the vertical behavior, where this time there is acceleration, and I've replaced a sub y with g, the acceleration due to gravity, which is downwards, so the negative, and the initial velocity, again, with the y component of the initial velocity. This should be enough to deal with all projectile problems, that you have these two motions going on independently of one another, but simultaneously, that it is the same time in each of these two equations. From the book, we get this equation, which of course is just this equation here, although instead of v sub I, they use v sub 0, the velocity at time 0. And this equation, which again is identical to that one there, so there's nothing new. But the book also throws in this equation, which is okay, but it's most unnecessary that you memorize that. That what they have done is gotten y as a function of x, and so you get the trajectory as it moves through space with y plotted against x instead of against t. But notice that all we've done is taken this equation, this simultaneous equation, solved it for t, and substituted it in here for t to get this equation. I think it is questionable whether you should try to memorize this equation when you can always get there by just the simultaneous solution of these two. The last equation that the book gives you, I would caution you against altogether. This R stands for range, and so the question is, how far away does the projectile land when you launch it with this velocity at this angle? But this equation is predicated upon the notion that the ball is landing at the same height that it took off from, that delta y here is 0. It may very well be that a projectile is launched and does not land at the same height it took off from, and this equation would fail you miserably. That what instead, just as for this equation, we solved for t here and substituted in, to get something that's workable as this equation, you would take this equation and solve for t and substitute that into here to get the horizontal displacement, or what was called the range. Note, when you solve for t, you will get two solutions, and you need to be mindful of which one is the one that is giving you an answer that is meaningful to you. Notice when delta y was 0, you also got two solutions for t, but one of them was 0, and that's a projectile that hasn't gone anywhere, so that wasn't of much interest. This then completes the lecture, and I hope it has not been too painful.